So in its global perspective, the Romberg integration method ignores the fact that many functions have regions of high variability and as well as sections where the change is gradual. Plus, the characteristic of the Newton-Cotes equations, which we discussed earlier on, is that the integral estimate is based on evenly spaced function values and that the base points are fixed. In other words, if we had a function that looked something like this, we would carry out our integration between these two base points, A and B. And obviously the base points are fixed and the errors are large. But what if we were able to relax this condition, the fixed base points, and position new points wisely enough to define a straight line that balances the positive and negative errors? And what I mean by that is, for our same function, we could position new points. Let's call this x0 and x1 at some function value f of x1 and f of x0, such that a linear straight line would be able to be drawn between them over an interval from -1 to 1 to balance the positive and negative errors. So the Gauss-Legendre quadrature method addresses this hypothesis in a way. And the objective of the Gauss-Legendre quadrature is to determine the coefficients of this setup such that the integration is equal to some coefficient multiplied by the function value f of x0 plus another coefficient multiplied by the function value at x1. Now we have four unknowns, c0, c1, x0, and x1, and we must develop four equations to resolve them. So we're going to use the following assumptions. Well, the first is that the integral, our integral method that we've just discussed, fits a constant line as well as a linear function exactly. That is, and this must be true if you think about it. If we have a constant line and we look at our integration method, it must fit this line exactly. And the same goes for a linear argument. That is, if we had a linear function, and this is x1, and this is x0, the integral would fit this exactly. And now we're working within standard limits of -1 and 1, and we're going to discuss that a little bit later on. Okay, but these two assumptions will provide, well, they provide us two equations, and we need another two. So the Gauss-Legendre method simply states that, well, the integral must also fit exactly a quadratic equation and a cubic equation, such that we end up with the following set of equations. the integral, which is equal to c naught f of x naught plus c1 f of x1 is equal to the integral between our standard limits, minus 1 to 1. We chose the standard limits because we want to make this a bit easier for ourselves, and this will have implications later on, of the constant value. We're going to choose this value of 1 multiplied by dx, and this value is 2. Similarly, we have it equal to, it fits exactly within the standard limits of our linear function, x dx, that is equal to 0, as well as our quadratic equation, and this is equal to 2/3, and our cubic relation. Which is equal to 0. Now if you solve this set of equations, you end up with the following. C naught equals C1, which is equal to 1. X naught is minus 1 over root 3. And x1 is equal to 1 over root 3. So this means that our integral simply becomes function value at minus 1 over root 3 plus the function value at 1 over root 3. But remember, we're working within our standard limits of minus 1 to 1. So we're going to have to generalize this. Well, we're going to have to translate our to our general limits. And in order to do that, we use a change of variables. So let's define a new variable and call it xd. Okay, so xd is our new variable, and we assume the relationship that our old variable x is equal to a naught plus a1 multiplied by xd. Now at our lower bound, where xd equals minus 1, we have that x is equal to a. Okay, that's from our trapezoidal rule. So therefore a must equal to a naught plus a1 multiplied by minus 1. And similarly at xd equals 1, x equals b, so therefore b is equal to a naught plus a1 multiplied by 1. This results in a naught equals b plus a over 2, and a1 equals b minus a over 2. In other words, x is equal to b plus a plus b minus a all over 2 multiplied by our new variable xd. So the derivative dx is equal to b minus a over 2 multiplied by the derivative of xd. In other words, if we had a function f of x and we wanted to change the variable to f of xd, this relationship describes how we do that. And then if we wanted to integrate our function, where we had the integral, say, of f of x dx, we would have to apply our Jacobian, which is, now we change in variable to f of xd, and we'd have to multiply by our Jacobian b minus a over 2 dxd.